Well, let's start today's lecture. Today I would like to start with a brief survey. Okay, our next topic is methods in mapping class groups which come from hyperbolic geometry, from Lobachevsky geometry. And to start, I would like to briefly recall some basic facts on Lobachevsky plane, which we will need to know. Okay, so I need, okay, Lobachevsky space plane or hyperbolic plane. The main, for our purposes, two models are important.
Можно не писать на крайней правой, или это будет мелко, мало?
Это будет плоховато. Лучше вот это вот.
Хорошо, тогда налево.
Все, отлично. Спасибо. Well, I recall two models. Vector model. We take pseudo-Euclidean space. Okay. It is more convenient to me to take one 0 square and two one negative square and two positive squares. Pseudo-Euclidean space R to 1, and in this space we have hyperboloid given by such equation. In other words, this is equation x squared 0 squared minus x1 squared minus x2 squared. So topologically, this is a two-pole hyperboloid, and one sheet of this hyperboloid is the model for Lobachevsky plane. This pseudo-Euclidean scalar product induces positive definite scalar product on every tangent plane, and it is a standard fact that this is a model for Lobachevsky plane, and the group of isometers of this Lobachevsky plane is an index 2 subgroup of the group of pseudo-orthogonal matrices. Index 2 arises since pseudo-orthogonal transformation can swap two sheets of the hyperboloid, and we are interested in those which stabilize this sheet. Okay, these are some standard facts. I hope that you more or less know them. If not, then okay, I hope you can recall them yourself. I will assume that we know such facts. Okay, and this metric induced on the Lobachevsky plane, it satisfies the most important thing, that it has constant Gaussian curvature equal to -1, and this is the main property for us. Okay, and the second model which will be important for us is Poincaré model. There are two versions of it. This is conformal model. There are two versions. Conformal model in unit disk and conformal model in half hyperplane or hemiplane, and in both cases the here we see lines. I recall that here lines in Lobachevsky plane, we need to take two-dimensional vector subspaces through the origin, and the intersection, so lines are hyperplane sections through the origin. Okay, and actually this conformal model is obtained in a similar way to the stereographic projection of a sphere. This is something like a sphere in pseudo-Euclidean case, and we take stereographic projection from this point, from the vertex of lower sheet of hyperboloid, and we get this model. What we need to know that here lines, straight lines, are arcs of circles which are orthogonal to the absolute. Absolute is here this unit circle, and here is this line together with infinity. And diameters are also lines, and here lines are also semicircles orthogonal to the absolute, and vertical lines. Okay, and I need explicit, I will need at some point maybe explicit formula for matrices. For Riemannian matrix here is given by this formula. I just recall it. I hope that if you don't know how to come from this metric to that one, then this is just an exercise. And in complex coordinate, we may write this as 4 dz bar over minus 1 minus modulo z squared squared. Okay, this is just if we introduce a complex coordinate z x plus y. This is usual unit disk on complex plane with center 0 and radius 1. And in this model of upper hemiplane, the metric is given by such formula. Okay, and the most important thing for me is how isometers of Lobachevsky plane look in these situations, look in this model. And again, I just recall the facts that in this model, in the disk, isometers, I will speak on orientation preserving isometers. It is easy to see that conjugation, complex conjugation, is an isometry. It definitely preserves this form. So up to conjugation, we may deal only with orientation preserving isometers. And if we here consider orientation preserving isometers, then we again get subgroup of index 2, but in special orthogonal group, pseudo orthogonal group with and here okay, here the this group of orientation preserving isometers is exactly the group of I again forget in which linear fractional transformations. I'm sorry, I always forget. Are they fractional linear or linear fractional? Linear fractional transformations. preserving, okay, in the first situation, we need transformations that preserve disk in the sense that they preserve disk as a set, the transformations of the whole, of the, not even of the, I recall that fractional linear transformation is always a transformation of extended complex plane with added infinity. Then it is one-to-one, provided that the matrix is ABCD is non-degenerate. And so we may consider those of them which preserve disk and those of them which preserve hemiplane. Those which preserve disk are isometers in this situation, and those which preserve upper hemiplane are as isometers of that model. And actually the the isometry between these two models is given by any fractional linear transformation that takes disk to the upper hemiplane. Okay, do I need to specify one such transformation, or it is clear how to produce it? Does everybody know? Is there somebody who don't know how to take disk to the upper hemiplane by a fractional linear transformation? Okay, if no, I skip this. Well, we just need to specify 3 points here, which goes here. Well, the thing which I don't want to skip is, let us recall which particular group of linear fractional transformations are these isometry groups. Okay, when a fractional linear transformation preserves unit disk. Okay, is the answer known? Yes. So, okay. I just for a moment I denote this by B2 and this by H2. These models. Just I need to specify something. So of course these groups are isometric to each other. But if I consider unit disk, then okay, fractional linear transformation is not the matrix given. It is given by matrix ABCD, but of course proportional matrices give the same fractional linear transformations. Hence, I always can consider these matrices up to multiplication by a constant, and this isometry group is just, I would like to recall that it is just pseudo-orthogonal group, a pseudo-unitary group, SU11, a special pseudo-unitary group, modular plus minus identity. Or it is called projective pseudo-unitary group. Okay, so I recall that a matrix belongs to this pseudo-unitary group if X belongs here, if X conjugate transpose to this matrix, X equals something like that. And in other words, any such X has form. These are exactly matrices of such type where modulo A squared minus modulo B squared equals 1. Okay, I hope all these things are more or less known. And in this model,
Можно вопрос? Меня еще немножко сбил. Она же изоморфная судьба, правильно? Просто на таком языке это проще написать.
Well, в какой группе?
Ну, SU11, она по идее изоморфна.
No, this group is non-compact, and that group is compact. So, no, by no means. Okay. I think that this is an important thing to understand, and I suggest that during the seminar we just recall this basic fact, which you just check that this is exactly that group. It is not difficult, but okay, maybe we this is not SU2. SU2 is okay. SU2 is related to three-dimensional sphere, to SO3, but here we have a pseudo-orthogonal group. So yes, of course, this group, I would like to be consecutive. So isometries of this model, okay, it is easier. A matrix preserves a real line if it is real, and it is easy to see that this is just SL2R, again modular plus minus 1, plus minus identity, and so it is PSL2R. Okay, and of course all these groups are isomorphic to each other, since these are different models for the same Lobachevsky plane. So these are basic facts that this is usually called SO prime. This is just the component, the connected component of pseudo-orthogonal group. We have two components. One of them swaps the sheets of hyperboloid, and the other preserves them. So this is isomorphic to pseudo projective special pseudo-unitary group PSU11, and this one is isomorphic to PSL2R. Well, the group. This is a connected the connected component of identity. In the group SO21, we have two connected components. One of them swaps the sheets of hyperboloid, and the second takes every sheet to itself. So we need those components which takes the upper sheet to itself. So this is one half of SO2. One half of this group. This is not very good notation, but still. Okay. And okay, what also we need is I recall I need two basic facts of differential geometry. One of them is usually included in standard courses, the other is not. Still, I don't think that we are going to prove it. I just mention it. The first fact, which is usually not included, as far as I know, in standard courses of differential geometry, is that every surface, every two-dimensional surface of constant Gaussian curvature -1 is locally isometric to the Lobachevsky plane. So every okay, this is just about two-dimensional Riemannian manifolds. Riemannian manifold. That is just with constant curvature I mean constant Gaussian curvature, of course. Is locally isometric. Locally just means that, okay, every point has a neighborhood which is isometric to a neighborhood of a point in Lobachevsky space. Is locally isometric to the Lobachevsky plane. It is not very difficult, but actually it has some it is not as straightforward as it may seem, but still there is such fact.
Свет из того, что есть накрытие, ну что ты будешь накрытие.
I would say that this fact implies that there is. I don't know how to prove it in the other direction. This is just some basic fact. Okay, we just look on metric, and if there is interest, we may maybe not today, but during some seminar look on this fact how to prove it. But it is a little bit distant from the total direction of our course, so I don't want to. This will take maybe half a lecture or something like that to prove it accurately. So, but still, it is true. And the second fact, which I hope is in standard courses, is Gauss-Bonnet theorem. Okay, if we have, I need this theorem in the following form. If we have some Riemannian surface with boundary, and this boundary has angles, we have it is piecewise smooth, and it is more convenient to me to consider exterior angles. So these are angles of rotations. And okay, this surface is of some topology, of some genus, and it is a piece of Riemannian surface with boundary and with angles. Then the general Gauss-Bonnet theorem says that
It's still compact.
Compact. Thank you. We will also want this for non-compact, but we will discuss this more carefully. We will need the case of surface with punctures. But this is later. The standard formulation is for compact surface. Then the curvature of, the integral, let this be omega. Then the integral of the Gaussian curvature over omega plus the integral of geodesic curvature of the boundary over the boundary equals plus sum of these exterior angles equals 2 pi over Euler characteristic of the surface. Okay, this is the general formulation. In fact, we will need only some partial case, and we are we do not need what is the geodesic curvature. We just need to say that if these are geodesics, or equivalently, we will need only the case of constant curvature -1. Then this is locally isometric to Lobachevsky space, and we do not need to know differential geometry to say what a geodesic is. Geodesic is just a piece of straight line in Lobachevsky plane. I will always, in situations we will consider, this will always be piecewise straight curve, so it consists of segments of straight lines. Then this is 0, the second summand is 0, and the formula takes the following form. So for a region in just hyperbolic surface is by definition surface of constant curvature minus 1. Just it is more convenient to say hyperbolic surface than surface of constant Gauss curvature minus 1. So for a region in a hyperbolic surface, the Gauss-Bonnet with polygonal boundary. So boundary is yes, and for a compact region, with if these are segments of straight lines, then the formula takes the form minus area. This is area of the region. This is 0, and here we have the same. Sum of these exterior angles equals to pi Euler characteristic. Well, in particular, for a closed genus G hyperbolic surface, we see the following. This one is also 0, since we have no boundary. And Euler characteristic is known to be 2 minus 2g. So we just see that area is 4 pi times g minus 1. And so hyperbolic matrix can exist only if g greater than 1. Hyperbolic matrix may exist only if g greater than or equal to 2. Okay. The next natural question is, do they exist or not? And actually the answer is that they always exist, and we will study the space of this matrix. But now let us start with the simplest example, just to give at least one example. It is somewhat more difficult to consider all of them. We will need some additional results but now we are already ready to produce one of such metrics. Okay, let us consider a Lobachevsky plane, and in this Lobachevsky plane we can consider yes, one important thing about conformal model, which I forget to say, but I hope you know it, is that indeed it is conformal. This means that angles here are true angles between curves in Lobachevsky matrix. So usual Euclidean angles which we usually see here are indeed true angles between these curves on the Lobachevsky plane. And hence, okay, it is not hard. We can consider regular n-gons on Lobachevsky plane. How to do this? Okay, we need to take just the most natural possibility to construct it. We just take the origin. This is not some special point of Lobachevsky plane. All points are equivalent, but it is a special point of a model. It is the most convenient point in this model. Let us take the origin and look on rays from this origin through angles 2 pi over n. And at each ray we take the point on the same distance. Okay, they are on the same distance in naive sense, and this is equivalent that they are on the same distance in Lobachevsky's sense. And now we consider n-gon with such vertices, but n-gon in Lobachevsky sense. Okay, an easy fact is that we may increase this distance. And an easy fact is that angles of this n-gon decrease as we increase this distance. For instance, this can be seen from Gauss-Bonnet theorem. Since the area increases, this is just 0. Oh, sorry, not 0. This is 2 pi. The Euler characteristic of a disk is 1, not 0. And okay, so this one should increase also. And these are exterior angles. So two limit situations are, okay, when a polygon is very small, then its dihedral angles are very close to Euclidean dihedral angles. I recall that or not dihedral, just usual angles. I recall that Euclidean angles of regular polygon are such. So generally this is greater than alpha and greater than, okay, and another limit situation is ideal polygon with vertices on the absolute, and then of course these angles are 0, since these circles are orthogonal to the absolute. So okay, alpha changes from this value to that. Since it changes continuously, of course it takes all intermediate values, and so there is, okay, so now I would like to take regular for G-gon, where G equals greater than or equal to 2. One, 2, 3, 4, 5, 6, 7. Oh, sorry, 7, 8. Okay, and I would like this angle to be 2 pi over 4g, which is pi over 2g. Okay, this is possible since as g greater than or equal to 2, then 2 pi over 2g is less than 4g minus 2 over 4g times pi. Okay, this is true. So this angle is indeed in between. So we may choose the size of regular polygon so that the angle of the polygon is exactly this. And now let us mark sides of the polygon as usually to produce to glue the surface of genus G. Okay, this is 3. 3.
Здесь цветные луки есть.
Yeah. But okay.
Можно вопрос, почему надо пилить на отображение? Мне казалось, надо прямые.
No. When we glue the sides of this polygon, according to these rules, all dihedral angles are glued, all vertices of this polygon are glued together. Okay, in all other points, look, here we have usual Riemannian metric. In any point on the segment, we have, from Riemannian point of view, we have half of a small disk on Lobachevsky plane. And we glue it with another half of disk. Okay, we glue again, get a good metric. But what happens in this vertex? In this vertex, neighborhood of this vertex in polygon is isometric to a segment of ball of disk in Lobachevsky space, in Lobachevsky plane, and this segment has this angle alpha. And we have 4G of such angles. If the angle is exactly this, then these 4G angles meet together so that we exactly get a smooth point with usual Lobachevsky metric. If not, then we have some singularity at the point. But if we choose alpha as here, then we get no singularity in this point. So we get usual smooth hyperbolic metric on our surface. This is the simplest example. This is not a general hyperbolic metric, but this is the simplest example. But okay, what can we say looking on this example? Actually, we can say a very interesting fact, which is more or less may seem to be obvious, but actually I do not know any proof without hyperbolic geometry. And the fact, theorem, is that the universal covering of the surface of genus G is homeomorphic, is diffeomorphic, let us speak in smooth category, is diffeomorphic to R2. Provided that G is at least 1. This is not true for G equals 0. Okay, the sphere itself is simply connected, so the universal covering is not R2. Okay, why this is true? Actually, this is general situation. The universal covering of any closed hyperbolic surface is even isometric to the Lobachevsky space. This follows from this fact. Okay, since they are locally isometric and they are simply connected, we just can construct this isometry, and the problems may arise only along some loop that, okay, passing along non-homotopic loops, we could arrive to different continuations of our isometry. But since we do not have non-homotopic loops, then knowing that we have, knowing that our hyperbolic surface is locally isometric to the Lobachevsky plane, we easily deduce that, okay, let us formulate explicitly the fact which I now prove, and Actually, I more or less proved it, but I would like to formulate it explicitly. The main theorem is as follows. Any simply connected complete hyperbolic surface is isometric to the whole Lobachevsky plane. Complete is very important requirement. Complete, okay, in usual metric sense, any Cauchy sequence has a limit. Why this is important? Yes, closed hyperbolic surface, of course, closed. Without boundary. But okay, we can just take some region, open region in Lobachevsky plane. Okay, this is a simply connected region. This is simply connected hyperbolic surface, which is not isometric to the whole Lobachevsky plane. But the matter is that if we, using this theorem, if we extend we have local isometry from some region in our surface to a region in Lobachevsky plane, where we can extend it since no problems arise along non-trivial loops. We have no non-trivial loops, so we may extend this to the isometry of the whole surface S. But now, if S is complete, then we necessarily have that the image is the whole Lobachevsky plane. If not, then the image may be some part of it, and even it may be not non-injective, and so on. Some situations may exist. But if we have complete, then it is necessarily the isomorphism on the whole plane. Окей.
Старшей размерности это неверно. Верно, что оно стягиваемым будет, но не факт, что это будет просто-напросто Лобачевское.
Нет, верно.
То есть вот этот факт, он...
Yeah, this fact is true in any dimension. If we have a complete smooth, without any singularity, without punctures and so on, if we can smooth closed hyperbolic manifold, then its universal cover is isomorphic to the Lobachevsky space, which is not true. Not true is any analog, no analog of this theorem. Okay, now this theorem for G greater than or equal to 2, since we have a hyperbolic metric, we see that it has its universal cover is simply connected hyperbolic surface. Of course, it's complete since we just take a compact surface and its universal cover, so it is isometric to the Lobachevsky plane, and in fact, in particular, it is diffeomorphic to Lobachevsky plane, but Lobachevsky plane is the interior of unit disk just from topological point of view. So we have diffeomorphism with R2. If G equals 1, then this proof doesn't work, but okay, if G equals 1, then the torus, the universal covering of a torus is diffeomorphic to R2 is very easy, and actually is proved in the same way, but we need to say Euclidean metrics instead of hyperbolic metrics. Okay, but in fact, it is not hard to see that we do not need this theorem. In fact, this theorem is somewhat not very easy, but actually we do not need it to prove this theorem. The matter is that for this particular hyperbolic structure, it is very easy to see that its universal covering is isometric to the Lobachevsky plane. We just need to decompose the Lobachevsky plane into regular. There are plenty of beautiful pictures, nice pictures in internet, but I can't draw this picture. It is difficult to draw hyperbolic pictures. But there is a very nice, since once we have a regular polygon with angle pi over 2g, there is a very nice decomposition of the total, of the whole hyperbolic plane into 4g gons, such regular 4g gons, so that exactly 4g of them meet at every vertex. So we can tile the whole plane by such gons, polygons, and after that we can, okay, hexagon is not good, we need to have 4g gon, but now we may mark these segments by A1, B1, A1 with such orientations and so on, and extend this marking over the whole tiling, so that to see that this is indeed the universal covering. So okay. Yeah. Yes, this is but only for this particular. It is not true that any hyperbolic metric on a surface is so nice. We will see more difficult pictures. Topologically, they are all the same. Okay, but of course, this is only one particular.
An action of the fundamental group of surface of genus G on the lambda 2, and this is its fundamental.
Yes, of course there are many other actions, and we get the same topological surface, but with different metrics. So there are plenty of hyperbolic metrics, and we will study this subject. But at the moment, to prove this theorem, it is sufficient to have a single metric.
Что вообще еще может получиться, кроме теоретически, кроме плоскости?
Не обещал, что она как и один.
Well, yeah. The corollary of this is that higher fundamental groups of surface of genus G are zero. Okay, higher fundamental groups, except for higher homotopy groups. Of course, this is not true for G greater than or equal to 1. Of course, this is not true for G equals 0. We have plenty of homotopy groups of two-dimensional sphere. This is well-known situation that we have many homotopy groups. They are not very easy and so on. And yes, until we have this corollary, we have no arguments towards that our universal covering should be contractible.
Но мы знаем, что это не сфера, правильно?
Yes.
Но может еще много чего?
Okay, we have no good classification of non-compact surfaces. We have good classification of compact surfaces.
Мы хотим классифицировать односвязанные поверхности. Их тоже нет? Накрывающая, универсально накрывающая, она односвязанная. Сейчас, правда, говоришь, что это односвязанная, прям плоскости и сфера. Сфера не подходит, потому что она компактная. Значит, сейчас, больше ничего.
I hope not. I'm not. Я не знаю. Вот, там надо смотреть внимательно. Не возникает ли там какой-то патологии, если мы какими-нибудь базовыми свойствами конечности пренебрегаем. Вот. Okay. Now some work on bugs. Last time I could not prove one fact, and actually I thought about it and I understood that actually I do not know any proof which doesn't use hyperbolic geometry at all. We need this fact, and we need hyperbolic geometry to prove this fact. And okay, I recall the situation. So last time we have proved that the geometric intersection index is well defined. We have proved the Beigen criterion, and we also have proved that isotopy is equivalent to homotopy for essential, for non-trivial, homotopically non-trivial simple closed curves. And in this proof there was one step where, okay, I had a bug in the proof, a gap, and now let us fill this gap. The situation was as follows. The gap was in the following particular claim. We considered a situation when we have two transversal simple closed curves on SG with and we knew that the number of intersection points of them can be decreased by a homotopy of only of alpha. We considered such situation. Can be decreased by a homotopy of alpha only. And I claimed that then there is a Beigen. So the problem was in this implication. After this implication, okay, then next steps, there were no problems in them, everything was okay. But in this situation, there was a problem, and I recall that the proof follows the following line. We considered a homotopy. Okay, the key claim is that the key condition is that the number of crossings can be decreased by homotopy. Then let us consider this homotopy, which decreases the number of crossings. So this is homotopy of alpha. So this is usual cylinder as one cross segment. We have homotopy of it into our surface, and we start from alpha, and we arrive to some alpha prime, and we know that alpha prime again is transversal to beta, and the number of crossings is strictly smaller than for alpha. Now we can make the total homotopy transversal to beta. Well, H is transversal to beta. Maybe made transversal to beta. And now we consider here the preimage of beta, and this is a submanifold transversal to the boundary.
Sorry, maybe there is through the isotopy instead of homotopy.
No, homotopy. This was before we proved that they're equivalent, and it was important for us to have homotopy here. The preimage here is some one-dimensional submanifold transversal to the boundary of the cylinder. So it may have closed components. It may have components which go from the upper base to the lower base. It may have such components. It may have such components. And now the next step is that, okay, we have at least one component of such type, since the number of crossings on the lower base is strictly greater than the number of crossings on the upper band. So we have at least one such situation. And then that bug arises. I just claim that, okay, it goes to a beigen, but it is not true, since the restriction of H to this beigen, this is truly beigen, but the restriction is not an embedding. There is no reason why it is an embedding. And now let us fill this gap. Let us complete the proof of this fact. So to do this, we need to go, well, I consider, now we do not need the total homotopy. Let us consider only this beigen. So we are
going to prove that it is indeed injective?
No, this one is by no means injective. But still we would find a beigen. Okay, we have this situation. We have this beigen. And we have its, I denote the restriction of H to this beigen again by H. I do not want to make complicated notation. We do not need any, all the other part is not needed to us at all. Okay, and what do we know? We know that H restricted to this one, to orange line, is injective and is a knock of alpha. Yes? And we know that H on the green side, here we do not know that is it injective or not, but here it is contained in beta.
Its image.
Its image, yeah. It is contained in beta. And now I would like to consider the universal covering of our surface. And we know, okay, the only interesting case is G greater than or equals to 1. If G equals 0, then no intersection indices at all, and no intersections in minimal positions, and okay, everything here is just is an exercise. So I always may assume that G greater than or equal to 1, and then this is R2. This is diffeomorphic to R2. And since this is a disk, we definitely have a lift of our mapping. Now, let us for a moment forget about our mapping and look on how the lifts of alpha and beta look like. How can lifts of alpha and beta look like? Okay. The lift of alpha is some collection of curves. Yes? What can we say about this collection of curves? Are these curves closed or not? The answer is not, but this uses an exercise which I asked you to try to perform last time, and we still have not discussed it. An exercise that the fundamental group of a closed surface has no torsion elements. If it had, then we would have closed components. Yes, we may have closed components. So okay, since if this element is has finite order in fundamental groups, then its lift is closed. But okay, for me it is not important now whether they are closed or not. So we have some. Obvious thing is that since this is a covering, any compact subset of R2 meets only finitely many of preimages and meet every of them by a finite number of compact segments, something like that. Of course, compactness says that we have such a good situation. So we have some collections of maybe closed, but in fact not closed curves, which are preimages of alpha. Preimages of alpha. And we have some collection of preimages of beta, something like that. Okay, what can we say? Sorry for such. It is better to say, okay, these orange are preimages of alpha. This is P, this is P1. And it is better to have green ones that are preimages of beta. Okay? Okay, what can we, this is just from general. But now, what can we say in this situation, since we have such a bigon here? Okay, as it is mapped to, since the restriction of H to the lower arc here is injective, it is also injective here. So we have such situation. Among this picture, we have such situation. We have this arc. Maybe it is intersected by several green arcs, maybe, I don't know. But now we have two intersections. These 2 points go to different intersections. Since this arc, the H tilde on it is injective. And we have here, okay, and now this green arc goes from that point to this one. It is not injective, but it is continuous. So we cannot swap between components. So this is the same component. These endpoints are mapped to the same component of the preimage of beta. So we have some picture like that. This component may behave ugly, but it goes here finally. Okay, so we have such situation. We have this one, and we have something nasty, but we have it arrives here. Okay, now this is not a bigon yet, but we may let me skip this as an exercise, since I don't want to go in these details and look through all cases, but an exercise that inside this situation we always can find an innermost bigon. So it is not hard to find that we always have a situation like that. Innermost bigon. What we need to use Jordan theorem here. Okay, the proof is something like that. Okay, suppose that this curve, if this green curve, if this green arc from this point to that point, if it doesn't intersect orange segment, then by Jordan theorem they together bound a disk. Okay, we are done. If it intersects, then we need to take the first point of intersection and look on something, and look on what happens before this point. More or less, this is a proof. Okay, this is the innermost beigen. Okay, is our proof finished?
Ну, вообще говоря, казалось бы, вот этот самый внутренний, еще, мы еще не знаем, что он, может, он не активен.
Actually not, yes. Okay, we see that now instead of this one was something difficult, but we have new beigen. We have new beigen which is here between two preimages. Now it is true beigen here, two arcs and disk between them. But now the next. An important thing here that I forget to say this, that we want to have innermost beigen not only between this arc and that arc. We draw here all arcs of preimage of beta and all arcs of preimage of alpha, and we would like to find innermost beigen in the total picture. So okay, if we have such beigen among two preimages, but we have another component of preimage of beta which goes like that, then we need to take this one, not that. So we took the true innermost beigen. The idea is that okay, on the boundary it is injective. When we go below, then we know injectivity on the boundary of this disk D, of this beigen D. Okay, now how to complete the proof? To complete the proof, we need another not hard but important theorem. It is Brouwer fixed point theorem. Suppose for a moment that we took the smallest beigen. No preimage of beta intersects here.
Ну типа если был бы не
Если бы был не инъективный, здесь были бы еще точки пересечения.
На границе, сейчас, мы хотим на границе.
Окей.
Желтая не могла с собой склеиться.
Потому что тогда здесь был бы целый период,
Там была бы еще...
и была бы еще точка пересечения. Okay, suppose that here there were 2 points x and y, which such that here we have this disk. On the boundary, projection is injective. And suppose that we have here 2 points, x and y, so that they go to the same point below. Okay? Now, let us remind that this is not just some projection. This is a covering, universal covering. And universal covering, the fundamental group of SG is realized as the group of deck transformations of the universal covering. So there is a deck transformation, по-русски накрывающая, накрывающее преобразование или преобразование скольжения называется, автоморфизм накрытия. Deck transformation. There exists a deck transformation that takes x to y. Well, but since this deck transformation must take preimages of alpha to preimages of alpha and preimages of beta to preimages of beta. So we easily see that, okay, the only possibilities are either, let us look on phi of the boundary of this disk. It may either take it to itself or take it to something that doesn't intersect with it. Actually, if phi is non-trivial, then it is easy to see that it takes it, that this is empty. Okay. This arc of beta is taken to some, this arc of preimage of beta is taken to some arc of preimage of beta, also without intersection points inside it. This is either the same arc or different arc. Yes? It cannot be the same arc, since deck transformation cannot have fixed points. And if we took segment to segment, then necessarily, independently of whether it preserves orientation or reverses orientation, it should have fixed point. Yeah? So, but deck transformation, non-trivial deck transformation, cannot have a fixed point. Hence, this green arc doesn't intersect with green arc. But it also cannot intersect with orange arc. Its image also cannot intersect with orange arc. This should be different arc. So they do not intersect at all. But now, okay, the only if two circles in plane do not intersect, then we have only two possibilities. One of them is like that. Actually, we have three possibilities. This is the boundary, this is phi of the boundary, or vice versa, or they are like that. This one is impossible, since, okay, here we have x, and here we have phi of x, and phi of x cannot be inside. Phi of x should be y, which is also inside here. So we have either this possibility or vice versa possibility when this is. We may replace phi by phi minus first, so that we get this possibility. This means that phi restricted to D is a continuous mapping from D to itself, the image of D. Hence, by Brouwer fixed point theorem, a continuous mapping of disk to itself has a fixed point. This is not isometry. Everything is just continuous mappings. But hence, phi has a fixed point, which is a contradiction. Okay, yeah. In fact, we could, yes. This is also possible. We could remind that we have hyperbolic metric, and the area also can be. So okay, this is just a different argument why this is impossible. But actually, here we have a fixed point, and hence it's possible, since the deck transformation cannot have a fixed point. So after all this, we get a beigen below. So in fact, it is not easy. Okay. We still have 5 minutes, yes?
Yes, 12.
Well?
12.
12?
До часу. Моим часам без 12.
Час 20 пора.
Да.
2 minutes. Okay. So these 2 minutes maybe maybe this is the time to discuss this question, but still other elements of finite order in the fundamental group of a surface or not. Yes, of course. If they are not in common, then they would be elements of finite order in homology, and in homology we have no such elements.
Сейчас, ну, у нас клиент P1 дает преобразование накрытия, правильно?
Yes.
Нет конечного порядка, то он называется тривиальный.
Почему? Нет, не тривиально. Преобразование накрытия конечного порядка.
Конечного порядка, да. Но их не бывает. Они бывают только эллиптические. Эллиптических нет, что не должны точки имеют.
Well, this is what I am going to discuss in the second part. I recall some facts that there are three types of of isometries, of orientation preserving isometries of the Lobachevsky plane. There are elliptic ones, hyperbolic ones, and parabolic ones. And elliptic ones always have a fixed points, so they cannot serve as direct transformations. This is a more difficult argument, which we will discuss on the next. I think that today it will be more like a lecture than like a seminar, but something in between. But in yes, and hyperbolic and parabolic elements are always of infinite order. This is why actually we would obtain, yes, well, so all elements of the fundamental group are of infinite order, or non-trivial. We could also obtain it in somewhat in the following way, that okay, suppose that the fundamental group is has an element of finite order, then we have this universal covering, but we also can consider finite sheeted covering. Just the covering corresponding, the universal covering corresponds to trivial subgroup of the fundamental group, and we take this covering corresponding to a finite subgroup, finite cyclic subgroup generated by that element of finite order. Then this is a finite sheeted covering, and if we take a point here in S hat, then above it has finitely many points. Then we could join two of them by an arc. By a deck there is a deck transformation that takes this one to that one, this one to that one, this one to that one, and so on. And there is proof like that. We could take some arc and take its image under powers of deck transformations, and more or less, again up to some technique, we get here a polygon which is taken by a deck transformation to itself. So again, Brouwer fixed point theorem says that it has a fixed point, which is impossible. This is not true proof, but we can proceed like that and get a good proof. Yes, and in fact, there is a purely homological argument that the universal covering it is the idea is that the Eilenberg-MacLane space for a group with at least one torsion element must be infinite dimensional.
Ты же сказал конечная группа.
Мы можем свободно действовать на всяком раз.
Yes, this is just this argument.
То, что ты сказал, неверно.
Почему?
Потому что глаза свободно действуют на эту бесконечность.
It cannot act on finite dimension.
Конечно, верно, стягиваемость.
But k by 1 cannot be finite dimensional. If pi has a torsion element, and okay, so so this contradicts this. Okay, now let us have a break, and after that we continue. Так.
Можно выключить звук за время. Сказать, на сколько времени перерыв, чтобы люди знали, когда включаться обратно.
I think break for 10 minutes.
Ну и можно.
Как здесь? Можете выключить?
Да, ну просто
Да?
Все. Не видно, и все.
Отлично. Well, let us try to proceed in English since we have this recording. Okay. I would like to...
Можно вопрос?
Yeah.
Я хотел вперед спросить, но забыл. Сейчас я правильно понимаю, что вот более-менее гиперболические многообразие это плюс-минус единственный способ получать как-то
Нет.
Есть еще какие-то?
Ну, по крайней мере, есть любые... Нет, в больших размерах многообразие отрицательной кривизны гораздо больше, чем многообразие постоянной отрицательной кривизны. По крайней мере, все они тоже...
Отрицательные тоже годятся.
Не положительные даже, да. Любой не... Да. Ну,
Примерно,
простой.
По-моему, то же самое.
Не, ну интуитивно понятно, что мы расходимся, гвоздички не пересекутся.
Да, ну а аккуратно надо доказать, да. Аккуратно это доказывается.
Не, хорошо, ну ладно, ну давайте их тоже на секунду назовем гиперболическими. Ну, то есть...
Ну, это близко, да. Нет, это не единственный способ, конечно, известные не такие.
Не буду. Кроме того.
Ну ладно, я могу потом рассказать.
Ладно, ну то есть еще
Правда, что если у меня есть просто многообразие отрицательной кривизной, я не могу там на что-нибудь там множить, чтобы оно стало минус 1?
Нет.
Не работает, да?
Гиперболически гораздо меньше. Это жесткая вещь, очень больше. Ладно, okay, well, let us proceed with our situation. Let us discuss for a moment isometries. Игорь, например, класс Пантрягина 0 у любого постоянной отрицательной кривизны. А у отрицательной что угодно бывает. Well, okay. So let us recall the classification of orientation preserving isometries of lambda 2. Okay. If we have a matrix, let it be X, in pseudo-unitary group SU11, then what can we say about its eigenvalues and eigenvectors? First of all, its characteristic, let it be A, B, B, A prime. Okay, any matrix has such form, and there are three possibilities. Its characteristic polynomial is always lambda squared minus trace of x by lambda plus 1, 0. Okay? And we have three distinct possibilities. If trace x, yes, trace x is always real, since it is a plus a conjugate, and we have three possibilities. And we may assume that trace is greater than or equal to 0, since we can multiply the matrix by -1, and actually we are interested in PSU11 in linear fractional transformations. We have situations trace less than 2, trace equal to, and trace greater than 2. Okay, here we have two real eigenvalues. Well, yeah, two real different eigenvalues. Positive, since we assume that it is negative, and their product is 1. So one of them is greater than 1, and the other is smaller than 1. Here we have two complex conjugate eigenvalues. So lambda and lambda bar, which with module lambda equal to 1. So they are on the unit circle. Why these situations are different? What can we say about eigenvectors? Usually, if we deal with not pseudo-unitary, but with usual unitary matrices, then we know that eigenvectors are orthogonal to each other. Is the same true for pseudo-unitary situation? Okay, now we consider, of course, now we consider pseudo-unitary scalar product instead of unitary one. Is it true that eigenvectors are again orthogonal to each other? So there is a standard fact that if we have unitary operator, then eigenvectors are orthogonal. Now we replace unitary scalar product, Hermitian scalar product with pseudo-Hermitian scalar product, and we consider pseudo-unitary operator. Is it true that its eigenvectors are orthogonal to each other?
Если уж сейчас все-таки вопрос, я все-таки еще с лекции не понял. Вот вроде матрица сигнатуры 1,1 и матрица сигнатуры 2,0, они на C, эквивалентны, в смысле, одна.
No. This is Hermitian matrices. If we have, this is not bilinear forms. These are полуторалинейный in Russian. I don't know how to say it in English, unfortunately. I never tried to say it in English. It is linear in one variable and antilinear in another. So if we have a Hermitian scalar product, then first of all we have its matrix in any basis. It has real numbers on diagonal, and we have the same situation as for orthogonal for usual Euclidean bilinear forms here. So we have positive inertia index and negative, and all the story repeats. The story, we cannot, if we multiply the form by I, it is not anymore. If we multiply a vector by I, then IXC equals XC, not minus XC. Since here I and here minus I goes. The thing, okay, if we speak about bilinear forms, non-degenerate bilinear forms, they are equivalent to each other, but not Hermitian ones. Okay, so this is different from usual Hermitian, but we have the same question. Okay, let us discuss the same question. For unitary matrices in Hermitian space, we know that eigenvectors are orthogonal to each other. Do we have the same fact for in case of a pseudo-Hermitian and pseudo-unitary case? Yeah, let us recall the proof. Yes, how this proof goes. If we have a unitary scalar product and a unitary matrix, okay, unitary operator or unitary matrix, okay, a unitary operator, then we can proceed like that. If we have, let Xc1 be eigenvector with eigenvalue lambda 1, and Xc2 be eigenvector with eigenvalue lambda 2. Yes? So we can proceed as following. This scalar product equals to lambda 1 xc1 xc2. Okay? This, on the other hand, this is equal to xc1 x xc2. Okay? What we see?
Это лямбда 2.
У нас это какой? У нас унитарный или
Мы сейчас
sorry. Unitary, not Hermitian, unitary operator. I'm sorry. Okay, we have x xc1, x no. It was correct for pseudo-Hermitian operators, but we are interested in pseudo-unitary operators. Then it is like that, and this one is lambda 1 xc1, lambda 2 xi2, yes? And this is lambda 1, lambda 2 bar, okay? Xc1, xc2. Okay. What do we see?
В первом случае они действительно ортогональны, получается. Ну, то есть если они...
Why? No. That's for a moment. Don't think about. In general, we don't see that necessarily xc1, xc2 equals 1. We see that we have one of the two possibilities. Either lambda 1, lambda 2 bar equals 1, and then we cannot say anything about xc1, xc2. Or xc1, xc2 equals 0. Yes? Okay. And now in usual unitary case, we also know another important thing, that a unitary operator has all its eigenvalues have module 1, have absolute value 1. Is this true for pseudo-Hermitian operators? Again, let us do a simple computation in the same flavor. But now take the vector with itself. So if we have an eigenvector xc with eigenvalue lambda, then we can consider x xc x xi, it is equal to xi. Well, it is non-zero. It is again lambda xi. It is lambda square, yeah. Absolute value of lambda square, since it's lambda bar. Xi. If the operator was usual unitary, if the scalar product was Hermitian, then this is non-zero, and we see that module, the absolute value of lambda is 1. But now we again see two possibilities. That either the absolute value of lambda equals 1, or xi equals 0. Two possibilities. Okay, and actually this easy example shows that all possibilities are possible. And actually, okay, if trace is smaller than 2, then we have real eigenvalues. So this one is not true. So these eigenvectors are isotropic. Can they be orthogonal to each other? No, since the matrix of the scalar product should be non-degenerate. If they are isotropic, then they are not orthogonal to each other. So here we have two isotropic not orthogonal to each other, isotropic means that scalar product with itself is 0. Eigenvectors. And in this
Ортогонал вектор, он двумерный.
well,
Сейчас у нас...
we are in two-dimensional situation, so there are only two eigenvectors. In this situation, they are isotropic, both are isotropic, and they are not orthogonal to each other. So this is not what we used to see in usual unitary situation.
I'm sorry. Don't we have real eigenvalues when trace greater, not less? I think let's switch.
Oh, I'm sorry. Of course, the signs are opposite. I'm sorry for that. Of course, if it's greater than 2, then we have 2 real roots, and if it is smaller, so it's vice versa. I'm sorry. Okay, 2 isotropic and not orthogonal to each other eigenvectors. And in this situation, we see, okay, here this is not 1. Okay, apart from the case when the matrix is identity or minus identity, there is not interesting cases. Yes?
Сейчас, но это не входит в этот случай, потому что...
Now case 3.
Да-да, но...
Lambda is lambda conjugate. So if we also have this one, then lambda squared is 1.
Да-да, но тогда след не меньше.
Yeah. So we do not have this. So they must be orthogonal. But now they cannot be isotropic, since if one of them is isotropic, then the matrix is degenerate. So here we have 2 non-isotropic, but now orthogonal to each other, eigenvectors. Okay, what do we see? This is the third. Second is something special. We will discuss it later. Okay, what do we see here? Here we see what is an isotropic vector. It's a vector. Now I don't need it anymore. What is an isotropic vector? An isotropic vector is vector of the form up to proportionality. It is a vector z1 with module z equals to 1, with absolute value of z equals to 1. Okay? Any isotropic vector is up to proportionality vector of such form. And what is this? When we act by x on z1, it is exactly the linear fractional transformation. It acts in such way on z. Yeah? So isotropic vectors are points on the absolute. So this means that actually any linear fractional transformation, any isometry of Lobachevsky space gives also a homeomorphism on the absolute. And in this case, we have 2 fixed points on the absolute. So this is case 1, 2 fixed points on the absolute. On the absolute. So our fractional linear transformation preserves these 2 fixed points. Hence, it preserves lines from these 2 fixed points, and hence this is just shift along this line, and this is called hyperbolic situation. We have two fixed points on the absolute, and any such thing is conjugate. It is better to look on this in the upper half plane model. Then we can make this up to isometry. We can make this line to be usual line x equals 0, and then any movement along this line, any linear fractional transformation, then preserves this line and that line. It is just a homotopy in usual. So it is just z goes to kz, where k is positive, real, and we see here all such lines are fixed by this transformation, and here these are arcs of circles through these 2 points, and these are equidistance of this line. These are lines which are on the fixed distance in Lobachevsky metric from this line, and they are so any such hyperbolic element can be included into a one-parametric subgroup of movements along the line. Okay, what we see in case 3? In case 3, what do we see? In case 3, we see that we have our linear fractional transformation has 2 fixed points, z1, 1. Again, we can normalize eigenvectors so that the second coordinate is 1. So z1, 1 and z2, 1 are eigenvectors. And then z1 and z2 are fixed points of linear fractional transformation. But what can we say now? They are not isotropic. In the case 3, they are not isotropic, so they are not on the absolute, but they are orthogonal to each other. What does it mean? It means that z1, z2 bar minus 1 equals 0. So they are not on the absolute, and this product is 0, is 1. Hence, one of them is inside the absolute and the other is outside. So exactly 1. We are interested in those which is inside the disk. Exactly 1 fixed point, not on the absolute, but on Lobachevsky plane. This is elliptic case. Again, by this one, it is better to look on it in model in disk. So we always can move this fixed point to the center. So this is just rotation around the point. And if we choose this point to be a center, then okay, this is just a usual rotation of a disk. Very easy situation. Again, this one is included in the one parametric family, one parametric subgroup. Okay, and these cannot arise as deck transformations. In any situation, they cannot arise as deck transformations since they always have a fixed point. And Now case 2. Case 2 is the most interesting. In case 2 we have both, we have eigenvalue 1, we have, it is root of multiplicity 2, yes? When a 2 by 2 matrix has eigenvalue, root 1 of multiplicity 2. We either have this one, which is not interesting in its identity, but in all the other cases we have the Jordan form of our transformation is non-trivial. Well, I am not. I don't want to go in details now, but a good exercise that any such. Actually, it is completely clear in upper half plane model. Then we have not a matrix in SU11, but we can look on corresponding matrix in SL2R. The trace is the same since it is conjugate. So this is all these cases are the same for SL2R. The traces do not change under conjugation. If we pass to upper half plane model, then we conjugate our matrix by some linear fractional transformation. Okay. Yes. Here we also have P-SU. Yes, and we may assume that trace equals 2, and again this matrix is conjugate to that one in SL2R. So our transformation is conjugate by particular transformation which is given by this particular matrix. What is this? This is transformation. Yes, this is transformation. Z goes to Z plus 1. Okay. So in upper half plane, we have this shift. This is parabolic example, and a very non-trivial parabolic isometry. A very non-trivial, very easy, but very non-trivial and very interesting situation here arises. Okay, we again may include this one into a one parameter subgroup. Yes? We can shift not by 1 but by 2 and so on. But in the cases of hyperbolic or elliptic, we have a real parameter. We have shift by some length and we have rotation by some angle. But here, all elements of this parabolic subgroup are conjugate to each other. All these shifts are conjugate to each other. Actually, they are completely conjugate to each other if we allow to conjugate by orientation reversing transformations. Otherwise, there are two types of them, right or left parabolic. Okay, and now let us return. This is some general story about Lobachevsky plane. Now let us return to our surfaces.
Параболический можно было просто геометрически видеть, что есть еще один тип.
This parabolic, one moment. This parabolic movement transformation preserves such lines in half plane, and in disk these are such lines, circles tangent to the absolute, and these are called Horner cycles. And an important exercise, which I hope you can do it, at least in this particular metric. It is not easy, it is not hard to check that the geodesic curvature of horocycle is 1. Okay, we understand in which direction. Of course, geodesic curvature depends on which normal vector is chosen. So, of course, here we have geodesic like that. So it is 1 if we choose such geodesic normal vector, and it is -1 otherwise. Okay, yes, this can be seen geometrically as well. Now, what can we say about deck transformations for? Now, first, let us start with closed surface. So, suppose that we have closed hyperbolic compact surface without boundary. So, let S be a closed hyperbolic. So hyperbolic surface means that surface with fixed hyperbolic metric. Hyperbolic surface, compact as usual. And we know that the universal cover is isometric to Lobachevsky plane. This is what we have discussed. But now the question is, so pi1 of SG, the fundamental group, acts by deck transformation on the universal cover. Acts, but okay, deck transformations are of course isometries, since they preserve lengths of all vectors. So this acts by deck transformations on lambda 2, and these are isometries. And we already know that these isometries never can be elliptic, since any elliptic isometry has a fixed point inside the Lobachevsky plane. Elliptic points on the absolute, fixed points on the absolute, this is, we do not see them in this picture. So these are not true fixed points. So it is not forbidden, but for deck transformation cannot have a fixed point inside this universal cover. So this is never elliptic. And a natural question is, so suppose we have here some element, oh no, not G, H. Well, and we consider here the corresponding isometry XH. And the first question, can XH be parabolic? Okay. Do we have any ideas how to?
Там как-то есть, там, мне кажется, есть проблемы с расстоянием, что параболические величины.
So I would like to announce that, okay, in fact, there is a proposition that in this situation, XH is always hyperbolic.
Сейчас вот у нас можем считать, что он примитивный элемент, правильно? P1. Значит, если кривая, да? Значит, если кривая, то P1 это 1. 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 Если кривая, то P1 это
Primitive means not a power of 7.
Значит, это некоторый кривой. Мы рассматриваем поднятие на кривой, она переходит сюда.
Кривая, but not simple. Not necessarily simple. Насчет простой кривой надо еще...
P1 элемент.
Не всякий элемент в P1 соответствует простой замкнутой кривой. Даже не всякий примитивный. Это не так просто. Какие-то можно реализовать без самопересечения, а какие-то нет. Not any primitive element can be realized as a simple closed curve. This is true. Yeah. Okay, for instance, you can take something like that, and you can take such. It is impossible to realize this element as a simple closed curve. Okay, let us start with the following observation. Okay, we have many elements, different elements of fundamental group. Yeah. At the moment, we do not know whether they can be parabolic or not. Okay, suppose some of them are parabolic, some of them are hyperbolic. Yes? To each parabolic element is assigned a point on the absolute. Each parabolic element has this distinguished point on the absolute. Actually, it is the unique eigenvector with eigenvalue 1. It is again isotropic in this situation. Okay, but to each hyperbolic element there are assigned 2 points on the absolute. And the first question, which I suggest to start with, so is it possible that this pi1 contains 2 elements, h1 and h2, such that xh1 is parabolic, xh2 is hyperbolic, and okay, it is parabolic, so it corresponds to some point p on the absolute. Yes? And this hyperbolic corresponds to a pair of points on the absolute. One of these pair coincides with those points. Is it possible, this strange situation? So let us proceed step by step. I would like to look how hyperbolic and parabolic elements are interact with each other, and we go to contradiction in several steps. Let us start with this situation. Is it possible that we have a parabolic element and a hyperbolic element, and they both correspond to the same point on the absolute? I would like to say that this is a very bad situation. This may never occur. And the question, what is bad in this situation? So one of them, we may always go to half-plane model and assume that P equals infinity. Just all pairs of points on the absolute are equivalent, so we may assume that P equals infinity and Q equals 0. Well, then parabolic element, okay, we may assume that parabolic element is just shift by 1. So xh1 is just z goes to z plus 1. And xh2 is z goes to kz. Okay, without loss of generality, we may assume that k greater than 1 just by replacing an element by its inverse, if necessary. Okay, is it possible that there? Yes, the idea is that for a group of deck transformation, we always, any orbit must be discrete. Yeah, let's look. If we have these two transformations, we may multiply our point by k many times, then shifted by 1, and then divided by k many times. And we return to a point arbitrarily close to the initial one. So we see that if we have these two transformations in our group, then the orbit of a point is not discrete. Which is not possible for deck transformation, is not discrete. So we lose discreteness here. So this is impossible. So if...
Честно, из этого следует вроде, что вообще не может быть одновременно параболическое и гиперболическое.
Why?
Потому что если бы у меня было одновременно параболический и гиперболический, то я бы один из них сопряг, так чтобы другой, чтобы он сохранял одну из точек.
Не, вы хотите сопрячь элемент, не лежащим тут. Тогда, конечно, можно, но это не элемент. Вот. No, there are no easy actually, I would like to announce one what we are going to discuss further. Actually, parabolic elements are not forbidden at all. It is possible to have parabolic elements, but in case when our surface contains punctures. Parabolic elements correspond to punctures. So it is possible, in case of surface with punctures, it's possible to have parabolic elements. So there are no easy way to get a contradiction here. So it is possible to have both hyperbolic and parabolic elements. It's okay. It's never, not with usual surface, neither for closed surface, nor with surface with puncture. This never can occur, since the deck transformation group never has non-discrete orbits. So this situation is completely bad. But the situation of just one parabolic element is not bad.
Сейчас у нас, если есть прокол, то сразу площадь бесконечная, да?
No. A puncture is still finitary. And
вообще как бы удаление точки, это площадь не
Нет, нам же полное гиперболическое многообразие.
No, меняет. Сейчас все обсудим.
Она точно имеет бесконечную?
Она точно имеет конечную площадь, да. Я как раз... I hope that we discuss this closed situation, and after that we proceed with the punctures. And the first thing which we are going to consider is, I would like to say that we always would like to have... let us do it now. In the case of a surface of finite type, now I would like to consider surface without boundary components. Boundary components will be later. But now without boundary components, but with punctures. If we have SGN, this is surface of genus G with n punctures. surface of genus G with n punctures. And now I would like to say which class of hyperbolic matrix I would like to consider. If I consider just all, it is a nasty object. It is okay. If of course I consider matrix on this surface with punctures, so the matrix outside the punctures. Yeah, but I would like to have some properties to have good properties of this matrix. To consider all of them, it's not good. It's just too huge set. Good class of hyperbolic matrix. Good class of hyperbolic matrix is like that. I would like to have hyperbolic matrix on this HGN, which are finite area and complete. Concerning completeness, we have already discussed. This completeness guarantees that the universal covering is again the whole Lobachevsky plane. So again, as Gn is its universal covering is Lobachevsky plane. But okay, finite area guarantees that our subgroup of isometries have fundamental domain of finite area. This is some tautology, but still we would like to have this. Okay, so there are situations when we have complete matrix, but it is not of finite area, and we don't like to study them, and they will be worse. But in okay, and in this situation, I just would like to announce the result, and now let us prove how to. Let us think together how to prove it. In closed situation without punctures, we have this proposition that all Dirac transformations are hyperbolic. In that situation, when we allow punctures, the claim is as follows. Well, here is surface with punctures, and when we have a surface with punctures, then there are special non-trivial homotopy classes. There exist such homotopy classes that they can be homotopy. There is a homotopy of these curves into an arbitrarily small neighborhood of a puncture. Around any puncture, there are two such homotopy classes of simple closed curves. Okay, since for each puncture there is a neighborhood which is just a ring, and in the ring its homotopy group is just Z, and there are only two primitive elements, so this is why exactly two of them. So these elements, which are these curves, which are can be by a homotopy made into an arbitrarily small neighborhood of a puncture. These for these homotopy classes, XH is parabolic.
Я правильно понимаю, что вот при вот этом универсальном накрытии у меня все проколы, они на границе, ну, как бы прям нет?
Yes, this is something like that, but actually there are no punctures here. So yes, there is. We can to a puncture here. We can it corresponds some But first we need to prove that it is parabolic, and then we can assign this point on the...
Я к тому, что вот эти вот петельки, которые вы нарисовали,
Yes.
это вот, собственно, сферы, которые...
Yes, these can be chosen to be horocycles.
Сейчас, вот можно, сейчас, пусть мы хотим доказать, что нет параболических движений.
Yeah, just one moment. I just would like to formulate that all others are again hyperbolic. In particular, we have such curves which again they become trivial after forgetting punctures. But this cannot be by a homotopy made into a neighborhood of a puncture, since it has several punctures inside. This also hyperbolic.
У нас есть параболическое движение, да?
Да.
Значит, у нас есть... Вот возьмем, ну, z и z плюс 1. И вы свой это все равно не помогает. Что у нас...
This is хороший вопрос. А можно ли да, может ли в каком-то другом гомотопическом классе быть сколь угодно маленькая кривая? Ну, он, вроде как нет, но он тоже не очевиден. Yes, this is one of the possibilities to try to prove this.
Точно, что на замкнутой поверхности у нас нет сколь угодно маленьких кривых, но не очевидно.
Ну, можно попробовать.
Не, вообще просто множество. Мы не знаем, что там геодезическое можно выделить.
Пока не знаем. Когда вот это докажем, то сможем, то тут же узнаем. Now, this is a good question. Suppose we have any Riemannian metric on a closed surface, just closed compact surface, and any Riemannian metric on it. Is it possible to have arbitrarily short, homotopically non-trivial curves? This is not so difficult. This can be proved. Yes. Even without any hyperbolic conditions. Just we have a Riemannian metric on a closed compact surface. Is it possible to have arbitrarily short homotopically non-trivial curves? Of course we have arbitrarily short homotopically trivial curves. But what about homotopically non-trivial curves? There is a very simple argument. Just no, this is not so easy, so good. The matter is that we have no idea why the minimum must be achieved. At least this is not so easy. This fact is much easier than the existence of the minimum. Совсем простой. Да. Прям вот совсем простой.
Нет, сейчас он как раз насколько угодно маленький, когда влезает в диск.
Да, у нас we have any point in a surface has a neighborhood homeomorphic to a disk. Since this is compact, we have finitely many of such neighborhoods which cover the whole surface. And of course, if the curve is very, very small, then it must be contained in one of these neighborhoods. And then it must be... yes, and it proves that this thing is not hyperbolic. Yes? Because, okay, suppose that it is parabolic. Then it is shift by one. This means that, what does it mean that adduct this shift by one? We may go to this standard model and obtain that this is this particular parabolic element. What does it mean? This means that if we start with some point here and shift by one, this z, and this is z plus 1. Then below, this is universal cover, but below this z and z plus 1 are the same point, and this segment goes to a curve in that particular homotopy class. Yes? This is exactly what does it mean that it is vector. But now we can take this z very far away, and we obtain arbitrarily small length of this curve. It is by no means, it is not geodesic or something like that, just some curve, some segment, but it becomes arbitrarily small for this particular parabolic element. So in this homotopy class we have arbitrarily small representatives. So it is impossible. And of course this one is of the same spirit. Here it is compact after filling punctures. Hence, we can obtain finite covering of these small neighborhoods of punctures, and all others are disks. We cannot have just finite covering of by disks, but we can have finite covering of disks and such neighborhoods of punctures. So if a curve is very, very short, arbitrarily short, then it is either in a disk and then it is homotopically trivial, or is in a neighborhood of a puncture. This is exactly, so we proved this one.
При этом у вас, я что ли, еще раз, я опять запутался. Мы при этом воспользовались тем, что универсальное накрытие лямбда 2.
Да, yes. Сразу этим пользуюсь, чтобы вы поняли все в лямбда. Да. Well, okay, this thing is true even if it is not complete. This part is true even if this part is not true. And now let us discuss this one. Why? We prove only one direction. If all others are hyperbolic, then yes. Okay. Vice versa. How can we prove that this particular curve going once around a puncture, that the corresponding isometry is parabolic? So this is the only thing which we still want to prove. What is the difficulty? A difficulty is that we have one-way implication. If a curve is short, then it is either in a small disk or in a neighborhood of a puncture. Yes? But vice versa, curves which are in arbitrarily small disks, they are of course short. But why a curve going around a puncture can be made short?
Если мы это докажем,
Если мы это докажем, мы получим, что параболик. Look, for a hyperbolic isometry, take any hyperbolic isometry. Take any hyperbolic isometry. Say shift along this. This point moves on some distance d. Consider a point here which is on some distance from our.
там дальше, не все.
Yes, it goes to a point which is the same distance from here. an easy exercise in Lobachevsky geometry that if we take a geodesic, or it is like that, and take the length of it, then it is greater than d. So any point, if we just take shift by d, then any point moves by a distance at least d. So if this is a deck transformation for some homotopy class, then there is a curve represented this homotopy class cannot be shorter than d. By the way, what we have proved? We have proved that any homotopy class with hyperbolic isometry contains a unique geodesic. Here is this geodesic. We may take any point on this line. Yes? Okay, we still haven't proved uniqueness. We still have some small, we still have to make some efforts to get uniqueness. But we proved that it contains this geodesic. Yes? We have proved that this geodesic is strictly smaller any other curve in our class. But maybe there is some geodesic which is not minimal. At least we...
Мы поднимем, получим какую-то кривую наверху, соединяющую точку и ее образ.
At least we need to care of it. Actually, it can be treated in a very simple way. Okay, if we have this another geodesic, we can take a point on it and
У нас же пока элемент P1, у нас конечная точка.
Actually, we always have conjugacy classes in P.
Да, но если у нас класс Just, то мы не можем сказать, что, короче.
If we have this minimal geodesic which we obtained, if we have another geodesic, then we take a point on it, and the same xh, or at least conjugate to it, since we do not care about a base point. It is the corresponding deck transformation is hyperbolic transformation corresponding to the two isometries with two hyperbolic transformations with different lengths cannot be conjugate to each other. These are different lifts of the same. Yes, one. Since we speak not about element of fundamental group, but about conjugacy classes, there are many conjugate lifts of it. Since only this one is the shortest one. Any other points, except for those which lie here, move on distance strictly greater than those. Hence, if we had another geodesic, it would be strictly longer. But this is impossible since two hyperbolic elements with different shifts are not conjugate to each other. Okay, but why this one is parabolic? Yes. Now, suppose for a moment that this one is not parabolic. So we have, since it's complete, we have that this is exactly lambda 2. Yes? Suppose this one is not hyperbolic, or parabolic, but hyperbolic. But then, just by our this argument, this homotopy class would contain a geodesic representative. Now, so we would obtain here hyperbolic metric with geodesic representatives. Which hyperbolic metrics on which are hyperbolic metrics on punctured disk with geodesic boundary? It is not hard to understand all possibilities. Let us consider so here we have, topologically, we have a punctured disk, one punctured disk, and we have geodesic boundary. Again, we can consider now for this omega, we can consider its universal cover. What is it? Again, look, the universal cover of this one is some line on hyperbolic plane. So we have just line on a hyperbolic plane, and the universal cover of this is exactly the half of the half plane. Obviously, it has. Now this half plane, we take the quotient by shift. By shift, or alone, we have here some length of geodesic. So we take, to obtain omega, we need to take quotient by omega tilde by z, which is shift by 1, or by some L. Exercise, just easy exercise on hyperbolic geometry. Area of this guy is infinite. So, infinite area situation, we cannot have such situation. So we see that just those propositions which I claimed. That in for these special homotopy classes, we have parabolic elements. For all others, we have hyperbolic elements, and so we have such nice situation. Next time we will discuss why the hyperbolic matrices always exist in interesting situations. And but now let us look on Gauss-Bonnet theorem. This is the last thing which I would like to discuss now. What can we say about Gauss-Bonnet theorem in this situation? So we have no geodesic representative here, but we can always choose here a horizontal representative, whose this is what we have discussed, whose lift is horizontal, and this horizontal representative can be chosen of an arbitrarily small length. Yes? Now let us, so we have this metric, this surface of genus G with n punctures. Let us look on these n punctures, and for each of them we take a very small horizontal representative of a very small length, and we consider this S. These rings are R1, R2, Rn. These small rings around this. Let us consider S prime Bs with deleted rings. Now this one is compact. Let us write the Gauss-Bonnet theorem for this compact surface. What we get? We get the R1, R2 are rings. Every such neighborhood is a ring topologically. Rings bounded by these curves. So we get, the integral of Gaussian curvature is minus area of S prime. Okay? Now we have here the geodesic, summoned with geodesic curvature. But let this be gamma 1, gamma n. Geodesic curvature is 1. Okay, actually, it is not hard to see that, in fact, if we look on this geodesic curvature from right side, then it is -1. But it doesn't matter, actually. We have here minus length of gamma 1 plus, since geodesic curvature is just 1, -1. Okay, so we have here the sum of lengths. And this is equal, we have no corners, and this one is, if we had some boundary with corners, okay, here will be also this. Here we have 2 pi over the Euler characteristics of the closed surface. Oh, no, not closed. Okay, Euler characteristics, it doesn't matter, of S and of S prime, yeah? Euler characteristic is the same. Okay, and now we can take the limit when gamma 1, gamma n becomes very small. This one is 0, and this one is minus area of S. So we have the same situation. The same situation. And again, the same Gauss-Bonnet theorem for, so punctures just give the impact to Euler characteristic. And we can write the same Gauss-Bonnet theorem. Yes, of course. Точку или диск все равно. У нас S, yeah, high of S is 2 minus 2g minus n, of course. So the area is different. It is not as for a closed surface. And actually we see here that a hyperbolic metric, a finite area complete hyperbolic metric, may exist only if Euler characteristic is negative. If it is not negative, then it cannot exist. And next time we'll see that in this situation, if Euler characteristic is negative, then such metric always exists. And we discussed this. But now just I would like to say that it is negative if either G is at least 2, then it is negative independently of the number of punctures, or G equals 1, or it is torus with at least 1 puncture, again it becomes hyperbolic, or it is a sphere with at least 3 punctures. So we have only finitely many exceptions. Well, okay, I think it's time to stop. Thank you for attention.
А может какой-то другой план доказать?